comment about the sophisticated definition.
Okay, thank you, Frick, and thank you, Jeremy and Rob, for the invitation. So I already spoke last year at the Lean Together meeting in 2019, but I don't think I can really start at the point where I left last year. So let me remind you what is this perfectoid spaces project. So with Kevin Buzzard, who is here, and Johan Commelin, we are mathematicians in the sense that we don't have any training in computer science. And I hope that this distinction between computer scientists and mathematicians will become less and less relevant when proof assistance will be taking over the world. But right now, it's still very clear who has computer science training and who hasn't. And so the first goal of the project was to have a team of mathematicians using a proof assistant and seeing whether how much assistance we need from computer scientists in a sense of people having computer science training, although they could also be called mathematicians for most of them, at least to my taste. And so we wanted to figure out this. This was the first question. And the next question was, mathematicians don't really notice that proof assistants exist. And we wanted to know whether it would make a difference if we formalize something which is fashionable. So we discussed with Kevin, and it was not yet Zulip, it was before Zulip time, and we both had the same idea that really the fashionable thing we should try was perfectoid spaces. And it doesn't matter what is a perfectoid space, and I won't use I won't use any knowledge about perfectoid spaces today in my talk. The only point is that people are excited about that, even if they don't know what it is. And that guy, Peter Scholze, got a Fields Medal for work that was possible because he invented perfectoid spaces. A Fields Medal in 2018, not in the 50s. And so we wanted to figure out whether a mathematician would notice more if we formalize something fashionable. That was the second goal of the project. And the third goal was to figure out whether proof assistants are actually capable of handling a sophisticated definition like the definition of a perfectoid space, or whether it was too complicated for computers. And now, what does it mean that this is a sophisticated definition? At the beginning of the project, we had a very easy answer to that question. You just ask a mathematician, just take a mathematician at random and ask, do you think perfectoid spaces are sophisticated objects? And the answer is yes. Okay. And that's a pretty efficient algorithm to decide this. And if you ask, is a group, the definition of a group, a sophisticated definition, then clearly the answer is no. But then at some point I wanted to, I wanted to give arguments, not saying mathematicians know that they are sophisticated. But then, of course, it's a bit a philosophical question, what is a sophisticated definition? So I could just say, oh, this is philosophy, I'm doing mathematics. But they've got this problem with this table, which says we are in the philosophy department. So I'm kind of cornered. So I hope that because I've got a proof assistant, maybe I could ask my proof assistant to prove that this is a sophisticated definition. So let's try first with a simple definition. This is not big enough. This is a definition of a group, and everybody agrees this is not a sophisticated definition. So let's see what is there. So this is a group structure on some type G is you give some multiplication and some notation for the multiplication map, so composition law, inversion, neutral element, and 5 axioms relating those multiplication and inversion and neutral element. I'm going to do as Cyril. Cyril, do you think I messed up the definition? Or do I have too many axioms? They sort of look like the definition of of a group, and we can ask Lynn about what's in this definition. And this is, so I wrote a bit of meta-programming code and asking what is in the constructor for my group. So my group.mk is the constructor for this structure. And you can see it says this is a constructor and there is this definition and there is a list of stuff used. Maybe I can point towards the, in particular you see the definition uses only equality and my group, the structure itself. So we can make a nice graph using this definition. And this is a graph that I get after running the output of links through a small Python library and then using this graph software. And I've got a nice graph saying that the group structure of my group depends on equality. But now this definition of my group is not what you would see in a textbook, in a math textbook. This is a computer scientist definition. You see, because the inverse map and the neutral element is part of the data. And this is not how we write it in a textbook, in math textbook. For math textbook, you would see this definition. So this is my other group. And the definition would be, I've got the composition law, and it is associative, and there exists a neutral element. And then on the next line, next line of the textbook, we would refer to E without really discussing whether we fixed some E or not. But so let's, if you want to convince Lynn this is a definition, we need to say, let E be some neutral element, and then the axiom for inversion is for all G's there exists H, and the same thing as before. Okay, so now you recognize the definition of a group in a math textbook. And let's look at the graph. Oh. So now this is what is used by my second definition. And we already see we are in trouble if you want to explain. I want Lynn to tell us whether the definition is sophisticated or not. And I've got two variations in the definition, and the graphs are, huge difference. So you see, it's not only that I use equality this time. I use AND, the logical conjunction, but also exists. And of course, I use what Kevin would call the computer scientist axiom of choice, because I said there exists a neutral element. And now if I want to use this such a neutral element, I need classical choice and non-empty and indefinite description, and I don't know what. And this ID right hand side, I think it's an artifact of the equation compiler in Lean or something like this. So maybe let's agree that we should get rid of everything which is really dependent on the foundation. So for instance, you see there is exist is in this graph, but not for all. So exist is the existential quantifier that we saw in the proof of in the definition that we have here. So there is existential quantifier used here, but the for all is also used and it's not seen in the graph because for all is part of Lynn's logic, whereas exist is defined as an inductive type and so on. So probably we should get rid of all this in the graph. So I've got a list of things I want to get rid of, which is completely an experimental list of things that I noticed that they show up, but they are not really relevant. And in addition, when we look at bigger graphs, such things create huge hubs because they are so useful. I mean, there's a huge hub with the existential quantifier connecting different areas of mathematics, but it's not very interesting mathematical statement that existence is connecting various areas of mathematics. I mean, if you say, Kevin likes propaganda about the Lagrange program relating different areas of mathematics, but maybe they should say existential quantifier instead. So let's get rid of this, but still we don't have a final answer for what should be the graph of my group. Because this is an isolated definition. This is not a definition in the context of a library. So here's the graph of group in MathLib. well, even after getting rid of the logic stuff, you see the actual graph in Mathlib, it contains, what is it all zoomed out? Semigroup and monoid and an instance of a monoid to semigroup, and all this is inside a group. So even if we get rid of logic and foundation, we still have variations, and I mean, it looks like a group suddenly become more complicated because it depends on a semigroup, monoid, and stuff like that. So it's really a difficult question. I don't have a good answer. This is the main point of claiming this is philosophy. I understand that I have the right not to have any answer. Only I need to try and let you think about this. So let's see comparison the definition of a vector space. So this is vector space.
This is after all the junk has been removed.
This is vector space after the junk has been removed. I think there is no longer junk. And so again, this is because it's in the library. It has everything. So it's also for Kevin, it has distrib sitting on top. So distrib is a mixing, as Cyril would say, saying that some law is distributive on some other law. So you see there are monoids. So the size of the labels is depends on how many things use this label. So you see that add monoid and add semigroup are very used, and ring is also pretty important, and so on. Okay, so we can try to measure complexity of a theory like this, and we can play and explore stuff. So let's see what perfectoid space is. And unfortunately, that computer is pretty slow. So this is a graph for perfectoid space. So this is everything that perfectoid spaces depend on, except that I noticed 1 hour ago during the break that something is missing from this graph, and it should be here. So probably my metaprogramming skills are so good that I messed up with the thing that is used to get this graph. And but okay, that gives you the scale of this project. And the interesting part is, I think, is the fact that there are many different kinds of mathematics. So you see on this corner there is natural numbers and integers, but here you've got filters and topology. But the big node here is topological space and lattices and partial orders. This is ring theory, probably. Over there you've got sheaves and more specialized stuff like Huber pairs, things that are really in the theory of perfectoid spaces, and so on. So it looks like Lynn agrees with me that this is a complicated definition. But then I wanted to compare with real numbers, and I was disappointed because, so it's in the other file. The real numbers, I mean, it's already very complicated by this measure. I mean, I think this graph is only about a quarter, is already a quarter of the size of the previous graph in terms of nodes and edges. And if you look at proof sizes, it's also pretty difficult to measure the complexity of the definition in terms of proof. Because I'm talking about definitions in the beginning, but the definition involves proving many theorems. So there are many proofs, but when I list the most complicated proof of the project, or the most complicated proofs that the project depends on, I see some of the expected lemmas that we think are complicated, but there are also completely random appearance of lemmas about lists, and we like about permutations of lists. So I don't know if it's because they are poorly proved or what, but at least, of course, lists don't appear in a textbook defining perfectoid spaces. The reason why lists are in the graph of perfectoid spaces that we showed earlier is because they are used by tactics that are used to produce proof, I think. You know?
Well, they would be used in the definition of finite.
On the definition of finite, maybe.
Finitely generated ideal definition.
Yeah, maybe. Yeah. there's some stuff like that. But so there is, in particular, there is a lemma about the permutation relation on list, the permutation relation on list, and one of the proof is huge, and I don't understand why. So, but at least we can say. So I never took a course in statistics, so I didn't try to make statistics. But probably the I don't even know the statistics word. I mean, how many long proofs there are compared to? I mean, the distribution of proof size in the project could be interesting to look at, but I don't know. So this is mainly that was the philosophical part of my talk, and I hope you can do better. I mean, I hope that someone who knows statistics and maybe someone who knows about graph theory too can come up with a better answer. But one thing that is clear from all this project is Lin is not so impressed by perfectoid spaces. And this is great news, because we won't use proof assistants to assist us. And if we have things that we think are very complicated, and the proof assistant tells us it's not so complicated, then it means maybe it could help us in the end. So I still, I could try to convince you that perfectoid spaces are sophisticated, because we published a paper about them with, and the advertisement was we formalized something sophisticated. So I could go back to the old ways of mathematician and use whatever time I have now, so half an hour, to just go over the full definition at maximal speed, and then you would probably be convinced that we did something sophisticated, but I don't think that would be very interesting. So instead, I know the second part of my talk would be about describing some formalization issues. So some stuff where we wanted to formalize something and it was not as easy as we wanted, and try to get some lessons from that. But I choose this example from the very beginning of the story, so that I don't have to introduce anything. So we now switch to elementary mathematics. Okay, are there any questions about all those graphs and philosophical issues? So it depends on the graph. In the beginning, the colors meant the kind of declaration, whether it's a definition or a lemma or stuff. But then in the bigger graphs, the colors mean, I asked this software, so this is a GFI, this is a graph visualization software. It's usually used to, I don't know, analyze Facebook communities or stuff like that. And so it has a function, compute clusters, and this is what the colors are. And also the spatial layout is automatic, which they just tell the software to spread the nodes and as if they were linked by strings and stuff like that. And this is all done by the software. So yeah, and it's sometimes interesting to see what ends up being in the same color, and for mathematicians, they are not necessarily. I can zoom in, but this computer is very slow, so it will be very painful. But yeah, you can zoom in and look at what are these. So, for instance, this is about orders and pre-orders, and well, you can explore this. If you have a reasonably fast computer, you can spend a lot of time exploring those graphs and probably deduce not much about, but it's a lot of fun. Okay? So, so now the main theme of the second part of my talk will be a function extension. So I start with a very elementary, so if you haven't followed anything from the first part of the talk, you can start again now. With very elementary mathematics. So I've got a dense subset of some Euclidean space, R to the P, and I claim that every uniformly continuous function defined on A with value in some R to the Q extends to a continuous function defined everywhere. So this is the most classical extension lemma for continuous functions. And I mean, versions of this lemma infinite dimensions are very important in functional analysis if you want to define integral or define Fourier transform, but this is already useful in elementary context. And in our context of the perfectoid spaces project, the most relevant example, elementary example, would be if you are building the real numbers and you have addition which is defined on Q, so from Q times Q to Q, but you see it as a function from Q times Q to R, and Q times Q is dense in R times R, and you extend it to the addition of real numbers. Okay, you need to prove addition, because addition is uniformly continuous and rationals, you can get addition of real numbers through this route. And I just want to say that the beginning of the proof of this theorem, it goes like this. You pick X in RP, you want to define F bar of X, you choose a sequence A with value in the capital A where F is defined and converging to X, because this is using that capital A is dense. And the key point is that uniform continuity of F ensures that the F of AN, the sequence, image of the sequence by F, is a Cauchy sequence. And so you get a limit Y by completeness. And you simply choose F bar of X to be this Y. And it's not hard to prove that Y is unique. And then the continuity, you need to prove continuity of F bar. But I just wanted to say that the first step is to get a candidate for F of X. And this theorem is not good enough if you want to define multiplication of real numbers. Because addition of rational numbers is uniformly continuous, but not multiplication. So you could get away with saying that multiplication is locally uniformly continuous or something like this, or inversion also doesn't work if you want to invert non-zero real numbers using such a theorem. This is not good enough. So let's get rid of uniform continuity and just get rid of the first part of the proof that I explained. I just explained half of the proof of the theorem, and I now want to put this first half of the proof as an assumption instead of being part of the proof. So I say, I've got a new version of this theorem. You've got a dense subset in RP and a function which is continuous on A, and you assume that for all x in RP, there exists a limit of f of un for any un converging to x inside A. So there exists y such that for all sequence with value in capital A where f is defined, if un goes to x when n goes to infinity, then f of un converges to this y. So be careful, there are two kinds of errors. The long errors are limits, and the short ones are function types. It's not so clear which one are long and which one are short. Sorry about that. And then f extends to a continuous function. Okay, and this time this applies to multiplication because you can check the assumption and you get multiplication. And this is all standard. But then, if we want to do inversion, then in real world mathematics, the inversion map is not defined at 0. 0 has no inverse. Of course, in proof assistant, the inverse of 0 is 0. But in real math, we don't say that. And so we need a more general setup where R is replaced by something more general. So in this case, it's really a trivial modification. But for the project, we also need more general topological spaces. So we want to have X and Y instead of RP and RQ. And in general, for general topological spaces, sequences are not good enough to explore the topology of a space. So you cannot use sequence limits of sequences only. You really need to use open sets and continuity. But you can still say that f of x converges to y when x tends to x0 while remaining in A. So before that, in the previous elementary context, I would say you take a sequence in A converging to x0, but no sequences are not good enough. But you can still say something like this. For every w, a neighborhood of y, there exists V neighborhood of X, so that for all A in the intersection between A and V, f of A is in W. So this is a definition of converging when X tends to X0 while remaining in A, which makes perfect sense in a general topological space. And now we can state what is the classical extension theorem. So this is the third version of the theorem we are discussing from the beginning. So you start with a topological space X. A is a dense subset of X. And I've got a continuous map defined only on A. So I need to assume something about Y. So Y was R to the Q previously. Now it has to be a regular topological space. But if you don't know what is a regular topological space, you just forget about it. This is a separation assumption. And then the rest of the theorem is the same. If f of x admits a limit in y when x tends to x0 while remaining in capital A, then f extends to a continuous map. Okay, so all the previous slides were introduction to reach this statement, which is in, for instance, in a Bourbaki general topology book. And this is what we had in the beginning when we wanted to formalize extending rings, as we saw with Q. I had a Q and R, and I wanted to extend addition and multiplication and inversion from the Q to R. But in our project, we need to replace Q by a more general topological ring. And the question is it good enough to have this statement in order to do this extension? Are there questions about this statement? Good. So does this theorem really applies to Q times Q inside R times R? Can I use this theorem in order to extend addition and multiplication from Q times Q to R times R? What do you think?
Yes.
Yeah?
Can we go back and have a look again? Might depend on what you mean by Q or something.
So here's a hint. Q is not a subset of R. You see, because I mean, there are many options to build R. But so maybe R is obtained using Dedekind cuts, or maybe R is equivalence classes of Cauchy sequences of rational numbers. But in all cases, it does not contain Q as a set.
You need to redefine Q.
So one option would be to redefine Q. So just forget about what Q was before, and then I define Q to be the subset of real numbers that happen to be rational. But then the next day I will define complex numbers, and then I will need to redefine Q to be a subset of complex numbers. And maybe Q is also a subset of periodic numbers. And then which one is Q? I mean, the Q that is a subset of two-adic numbers, or the Q which is a subset of C. So that's not good enough. So for formalization people, this is already a clear indication that something is wrong with the theorem that we had before. I mean, this theorem is not applicable to any example we care about. Okay, so maybe a better framework would be to say, instead of having A is a subset of X, I've got an injective map I from A to X. So this hook at the beginning of the arrow means injective. So I've got injective map from A to X, and I've got F, which is defined on A. And what I'm looking for is the dashed arrow extending, not in the sense that this diagram commutes. Okay? So let's say this is what people mean in the previous theorem. But this is frightening because if we start keeping track of inclusion maps, then maybe when we want to discuss inversion, so we've got the inversion map on Q, and we want to extend it to R star, non-zero real numbers, and now maybe I need to consider this diagram. Like I've got my inversion is only defined on Q star, non-zero rational numbers, and then I've got inclusions all over the place, and I need to do diagram chasing in this everywhere. And we did that for some time in the project, and it's not undoable. But you see, every time every time there is a small complication coming from formalization, you can be really worried that it will pile up and things will get out of control. But still, I mean, we can't avoid having that, but we'll need something else to avoid propagating the mess. So now there is a side issue. How do I formally refer to this F bar? So you see, real-world mathematics is full of sociological promises. Like in real-world mathematics, what happens is if I write F bar, it means I checked the definition, the condition of the theorem. I check the assumption, and the theorem gives me F bar. But so maybe the way the Ling or any proof assistant, really nothing I'm saying is specific to Ling. Maybe I would say I just extend, and then this extend function takes 4 arguments, f and I, that are my map, a proof that I is a dense embedding. So that would be the map analog of being a dense subset. And H is a proof of the fact that for every x, f of x admits a limit, etc. So that would be 2 proofs to carry around. And this looks heavy to write each time I want to mention F bar. And I know there is a standard trick in proof assistant is to use implicit arguments. You see, I and F can be inferred from the types of D and H. And then it means, how should I denote the extension F bar? I should denote it by something that doesn't mention F at all, nor I, but only the proofs obligation that I had. And at some time in the project, I had such a definition, and this is where I stopped, and I thought something is really wrong. And no, I don't want to do that. And so a better solution, which was already Massot before in this context, I guess was written by Johannes, probably. Where is he? Yeah. Is to say, okay, I don't care about the assumption, especially on F. I will just define an extension operator, E sub I, and so extending with respect to I a function F, what does it do? It takes some X, and if there is a limit, then I just choose one and define this to be the extension, and otherwise I just return some joint value, and this way I don't have any proof obligation when I want to just mention F bar, which would be this EI of F. And this is almost not using anything about I. Actually, if I'm ready to assume that Y is not empty, I can just use this definition by using the joint value provided by the assumption that Y is not empty. But if you don't want to make that assumption, the fact that the image of I is dense and that X seems to be non-empty since I've got a value to evaluate then it allows to prove that Y is non-empty. But anyway, so now I can write so the proof of the fact that I is a dense embedding dot extend F, and that's reasonable thing. And I think this is a very general lesson you can use in formalization. So I'm sure this is really very well known to experienced formalizer, but for mathematicians who want to learn the tricks, I think it's useful. Now there are also separation issues in the project. Because we wanted to use rings, topological rings, instead of Q, topological rings that are not metric spaces, so I've already discussed that, but also that are not separated. So there can be 2 points, such that any open set containing one of the points contains the other, but still they are different points. This is what it means that the ring is not separated. And there is a notion of completeness of a topological ring that I discussed last year, but you don't need to know what I said last year. I mean, you can build some R hat, which is a minimal, complete, and separated space. So minimal, I don't have time to explain, but complete and separated, and a map I, so just like the inclusion map, from R to R hat, and we want to extend addition and multiplication in the sense that we were of the previous slide. So I should factor through I multiplication and addition on R hat. But the issue is that this I map is not injective in general. So earlier I said instead of having a subspace, I've got an injective map, but here it's not even an injective map. I've got a map, but it's not injective. So you cannot even pretend that R is a subspace of hat R. And this happens whenever the singleton 0 is not closed in the ring. And the standard solution that is used in Bourbaki general topology is to say, okay, first I make R separated by quotienting out by the closure of 0. And this is clearly a ring because the closure of 0 in a topological ring is an ideal. And then you need to negotiate with continuity because the algebraic library which says this is clearly a ring because I'm mod out by an ideal is on one side, and on the other side of the story you've got the topology library which says that because this is a quotient, the minimal quotient that makes R separated, I know a nice topology to put on it. But from a formal point of view, those are two different types. The quotient by an ideal and the quotient by the separation relations. And they are, of course, they are isomorphic, but on one side I've got the algebra and the other side I've got the topology, and it's not as easy as it should be to get both on the same side, but okay, it's okay. And then what is the standard solution is just to redefine R hat to be R prime hat. So I do it in two stages. First, I make it separated, and then the would-be inclusion map of R prime inside this completion is indeed injective. And if you do the hat thing, after doing the prime thing, it doesn't change much, the fact that you put a prime first. And in the real-world math, this is very easy to handle. You just say that the completion R hat is both R hat and R prime hat. You just pretend they are the same thing, and then everything works. And what is fun is, if you do that, if you want to redefine this completion by doing this first quotient, even if the original ring is already separated, taking this quotient gives you a different set. And this is not an artifact of type theory. Even in ZFC, if you take a set and you've got the trivial equivalence relation where a point is equivalent to itself and nothing else, and you do the quotient, you get a different set. Because instead of having the set of x that belongs to R, I get the set of singleton x for x in R. And so even in set theory, it doesn't work, this trick. And even if you start with a topological ring that has no separation issue at all, you still have two different ways of defining the completion. And so we were worried about that, and I started thinking about maybe we shouldn't be too attached to a single definition of completion of a topological ring. Maybe I should find an abstract predicate of a pair of topological ring and a map between them that will ensure that they have all the right properties for being the completion. And I started to think about what was the abstract characterization, and I found something that was promising. And when I set out to prove that it worked, I realized that I needed a version of the theorem, the extension theorem for function, without any injectivity assumptions. And so it seemed that I was stuck, because my extension theorem that made me, that required having an injective map was now blocking me from putting all those difficulties under the rug. But then I went back to the proof of the theorem, and I realized that the injectivity assumption was not used anywhere. And the final version of the extension theorem is exactly the same, except that, this is a typo, this is not injective. I return to so there's no longer a ring, I return to the abstract topological space thing, and say I define EI without any assumption of I if I assume that EY is not empty. But then there is no assumption on I at all. And if for every x1 in a neighborhood of x0, f of x tends to a limit when x tends to x1 while remaining in A, then the extended map is continuous. And what is funny is there is no assumption at all on I, but there is no assumption on F. There is no continuity assumption on F. But the trick is, in this version of the theorem, I never said that the extended map extends F. And if I apply it to values that come from A, okay, so if I add assumption saying that F is continuous and I push back the topology of X to A, then I've got the full extension theorem and it works as advertised. So really the lesson, so there are a couple of things about subtypes and formalization issues that come up very often that you can remember if you're a beginner. But the main point I wanted to make here is that thinking about all those formalization issues actually led us to improve the theory. And we proved this theorem with exactly the same proof as before, essentially, but with less assumption because we were annoyed by formalization issues. And the conclusion was not that formalization was bad. The conclusion was that Bourbaki was not general enough, not abstract enough. And by the way, no, I don't have time. I see Frick is getting nervous. But so by the way, a little bit of side propaganda. The assumption of the theorem can be written like this. For all u neighborhood of x0 and for all x in u, there exists y. In y, there exists w neighborhood of y, there exists v neighborhood of x, so that for all a in A, I of A is in V implies f of A is in W. So this is the elementary assumption of the theorem. But in MathLib, this is not written like this. This is written like the set of x, so that there exists y, such that push forward by f of pull back by I of the neighborhood filter of x is less than the neighborhood filter of y, belongs to the neighborhood filter of x0, which is much more efficient and concise. And 2 years ago, I knew nothing about filters. And I've been a professional mathematician for more than 10 years, and I learned filters in MathLib. And when I wanted to prepare this talk, I thought, what can I explain in 45 minutes to a room of people, and some of them maybe don't even know what is a filter? And what can I do? And that would have been me 2 years ago. So that was propaganda for pull back and push forward and operation and filters. So now a last slide about final assessment of the perfectoid project. So remember the goals we had. The first goal was to check whether we could use a proof assistant as mathematician. And indeed, we've been able to do that without hiring computer scientists.
You need a lot of help.
And of course, but of course, we needed help. We used Zulip a lot, asking for help. So we still can't do it autonomously, but at least we could do it. Some mathematicians noticed. So I had colleagues who saw the paper on arXiv and told me it was really cool that someone formalized perfectoid spaces. And we received people that asked us to write, I don't know, semi-popular science papers for the notices of the AMS or the English thing or the French thing analogous to the notices of the AMS. So it was indeed noticed by a mathematician. I won't say that every mathematician in my department started using a proof assistant after knowing about that, but still there was some effect. And the computer scientists, or at least the formal proof people, also noticed it. And there will be a paper in CPP, so Certified Programming Proofs, in 2 weeks in New Orleans. So it's also good news. I mean, this community of formal method is welcoming to mathematicians. I mean, we wrote out the paper the way we thought that it would be interesting, and they are happy. So that's good. And we did contribute to Massot, but we have a huge backlog of things to merge. So in terms of library development, we had some effect, but it's still difficult. In the repository, we have a folder called formathlib, full of things that were meant to be PR. So that will be probably also part of the discussion at the end of the week, how we could improve that. And then the last point is that the big projects are good. I think it was really good to have a project. But when you're mathematicians and you say, I want to learn how to use proof assistant, and if you just set out to formalize all the undergraduate curriculum, for instance, this is hopeless. And of course, all of modern research, this is much more hopeless. But if you just get a target and focus on this and build a library as you go, I think it is a really nice way of going. And so we need the next target. And the one I propose, because originally I'm not doing algebraic geometry or general topology and uniform spaces and stuff like that. I'm working in differential topology. So the thing I think would be a very good next project is to formalize some flexibility result in differential topology. And I'm sure many of you have seen on YouTube's videos of sphere inversions. You know this game, you start with a sphere in R3, and it is painted in one color on one side and another color on the other side. And the game is to turn it inside out without tearing anything. I think I've got a video somewhere, and I promise I'll stop. Yeah. So is it playing? Yeah. So you see, and you are allowed to have self-intersection, but locally it should be a smooth surface. And so you see that they are doing something crazy. And at the end of the game, at each point, the surface is locally embedded in space smoothly, and at the end of the process, this is turned inside out. And I claim this would be nice to formalize a proof of existence of this sphere inversion, because many mathematicians I talk to think that proof assistance can be used only for algebra and combinatorics, because they think this is what computers understand. And this is very funny, because they say things like, no, you know, infinite stuff you cannot make in a computer, so probably this is why Fay-Thompson has been formalized, because it's about finite groups. And I always answer, but do you have infinite process in your brain where you're thinking about infinite objects? But somehow this argument is not good enough. So I think we need, of course, what we just heard by Fabian was great in this direction, proving that the proof of Poincaré-Mednickson, which is based on sketches and really pictures, can be formalized is already great. But I think we should go for such a target next.
We're 10 minutes into lunchtime already, but I'm sure there are many questions. Let's have 3 questions and then go for lunch and ask the other questions during lunch if you can. So, are there any questions? No questions, let's have lunch.
You're really hungry,